Welcome everyone. We're going to work on this redox problem here. So I'm going to read out the problem before we actually start working on this question. So the problem says a voltaic cell utilizes the following reaction and operates at 298 Kelvin. And the given equation is 3 cerium 4 plus aqueous plus chromium solid gives you chromium 3 plus aqueous plus 3 cerium 3 plus aqueous. Calculate the net potential under standard conditions and when chromium 3 plus concentration is 0.5 molar, cerium 4 plus concentration is 2 molar, cerium 3 plus concentration is 0.05 molar. So this is the problem that's given. So the problem, when you read the problem, obviously the problem has two parts. One is we have to calculate the net potential under the standard conditions. So that's what it's asking you to do right over here. And then it's asking you to calculate the potential under these concentration conditions. Okay. So that means it's saying for the first half of the problem, calculate things under standard conditions, and then for the second half of the problem, calculate it under non-standard conditions. So that's what this is actually saying. Okay, so let's go through the steps and then do this one by one. So first thing we're going to address is how to calculate the net potential of the reaction under standard conditions. So in the first step, just like as we have done in our other problems, our goal is to identify the key reactants and products. That is, we want to look at the left side and then try to match to things on the right side. So for example, if you have C4 plus on this side, then that should lead to the formation of C3 plus, because you can completely change the element. If you have one type of element, the other element should come from the same element on the left side, right? Same thing is true of the chromium. So we have chromium and solid, and then on this side we have chromium 3 plus. We kind of have an idea that somehow this chromium 3 plus on the product side should have come from the chromium on the reactant side. Okay, so that means the chromium and the chromium 3 plus are related, C4 plus and C3 plus are related. And the question is, how do we match them, right? So first, let's just identify them and make a mental note of it. The second thing that we're going to do is we're going to try to match these pairs to things that we see in the table of standard reduction potentials. In the table of standard reduction potentials, you're going to see half reactions which connect cerium 4 plus to cerium 3 plus. You're going to see reactions that connect chromium to chromium 3 plus, and then you just match it to that, and then you just write down what those reactions are. Okay, so match it to them, and in step 3, we're just writing down the reaction as it is given in the table. So in the table, you will see that if you have the standard reduction potential table, you'll see that chromium 3 plus 3 electrons going to chromium, and its E naught is negative 0.74. So you'll see that in the table. You write it down as it is. And then for the cerium 4 plus, you'll see that cerium 4 plus electrons going to cerium 3 plus aqueous. And then the E naught for that is positive 1.61 volts. And this will be given in the table. You just write it down as it is. Okay. So once you write it down, in the next step, what we're going to do is between the two reactions, we're going to decide which one should we keep as it is and which one we need to flip. And that depends on what is given in the overall reaction. Okay, in the overall reaction, we see that there is cerium 4 plus on the left side, and then we are comparing that to the cerium reaction that we just wrote down, and we see that the cerium 4 plus is on the left side, and the corresponding cerium 3 plus is on the right side, and the corresponding cerium 3 plus is on the right side. So we know that the second reaction, we're just going to keep it as it is because it matches exactly what is given in the overall reaction. But if you look at the first one here, we have chromium 3 plus on the left side, whereas the chromium 3 plus in the overall reaction is on the right side. And then the chromium in the half reaction is on the right side, whereas the chromium solid is on the left side. So that tells us that we have to flip the first reaction and then keep the second reaction as it is. Once you flip one of the half reaction, it is very clear that that is what is going to serve as the oxidation reaction. Okay, so this is the reaction that is undergoing oxidation once you flip it, and then the other one is going to undergo reduction. So this is the one that is going to undergo reduction. Okay, so we're going to go ahead and then actually flip the reactions. So you can see that in step 5 we've flipped it. When you flip it, the first reaction has been which we decided to flip. You can compare the chromium reaction here to chromium reaction here. We have flipped it in the steps in step number 5. So once you flip it, you also have to change the sign of the voltage. So we have changed it from negative to a positive. So we write it down and just keep it. Okay. And then there's one crucial step which we have to do before we write the overall reaction. That step is going to be, we have to make sure that the number of electrons are the same in both reactions before we start adding things together. We know that the first reaction already by its nature has 3 electrons. We have 3 electrons here, and we can see that there were 3 electrons. But then the problem was the second reaction had only 1 electron here. So if you want to make the number of electrons equal, we're going to multiply this whole reaction by a factor of 3. So if you multiply the whole reaction by a factor of 3, you would end up with 3 cerium 4 plus 3 electrons, giving you 3 cerium plus. And if you remember in the second problem that we did in this video series, whenever you multiply an equation by a factor, you never multiply the voltages by that factor. So you just leave the voltages as it is. Don't multiply the voltage, just multiply only those equation part. Okay. So once you multiplied it, we're just going to add the two reactions together. When you add the two reactions together, we see that when you add the reactions together, there's 3 electrons on the right side, 3 electrons on the left side, so we can cross them out. Those things are not going to show up in the overall reaction. Everything else is going to show up in the overall reaction. So we have Cr, so you can see that, so there's actually, this is an error, there should be no 2 there, there should be Cr. So you can see that there is 3 Cr4 plus, which comes from here, and then there's Cr solid, there's Cr solid, we have it here, Cr3 plus here, Cr3 plus here, and then Ce3 plus here, and then Ce3 plus here, 3Ce3 plus, everything shows up there. And then when you add the two voltages, you're going to see that the total voltage comes out to 2.34 volts. So that's the net potential of the reaction. This is the net potential of this redox reaction under standard conditions. We say it's under standard conditions because we have manipulated only E naughts, right? E naughts were all measured under standard conditions. So therefore, delta E naught is also measured under standard conditions. So we get the net potential of the reaction. So we have the net potential now. Our next question is what? So we've achieved the goal, the first part of the problem. We know what the net potential is under standard condition, which we've figured it out. And that's the value of delta E naught that we've calculated. But in the second part, it says calculate the potential also under these conditions, and these conditions are non-standard conditions. So the net potential that we're going to figure it out here, that's going to be called as delta E and not delta E naught. Okay, so this is delta E and this is delta E naught. I'm going to rewrite this one more time. This is delta E naught. Okay, so this is delta E naught and this is delta E. So the next goal is going to be how to figure out the delta E for those reactions. Okay, so how do we do that? So calculating the potential under non-standard conditions. If you want to do that, we have to use the Nernst equation. This Nernst equation is something that we discussed in the part 3 of the redox reaction basics video. And in that video, we said that if you want to figure out delta E, which is the potential under non-standard conditions, this is the delta E, which is the net potential under non-standard conditions. It is going to be related to delta E naught, which is measured under standard conditions, minus this particular term, negative RT over NF ln Q. Okay, and what are these terms? R is your gas constant, which is given here. T is given here as 298 Kelvin because the problem says that the temperature is 298 Kelvin. And then the F value that we need is already known. It's Faraday's constant, which is 96,488 coulombs per mole. N that we are going to plug into this equation is the total number of electrons used to balance the two reactions. It's 3 electrons here, 3 electrons here. So we know that our N value is 3. So we know the value of R, we know the value of T, we know the value of N, we know the value of F. The delta E naught value is something that we figured out here. So we can take this delta E naught and plug it in here. So we know delta E naught. So the only thing that we need to figure out is what is this Q. And we know ln is natural log. So once we know what is Q, we can take the natural log of that value. Okay. And if you remember, Q that we have written over here is called reaction quotient. We talked about this in the reaction basics, redox reaction basics video. So this is called reaction quotient. And we know that reaction quotient is typically written as the ratio of product concentrations of your equation of your chemical reaction divided by the reactant concentration of your chemical reaction. Okay, so that means, so we can figure out the value of the product concentrations and reactant concentrations, put it in the place of Q, and then we will know what it is, right? So we're going to simplify this further. So if you simplify this further, if you look here, look what happened to Q. The Q has been written like this. Q has been written as Cr3 plus times the concentration of Ce3 plus whole to the power of 4. Where did this come from? So if you look here, Cr3 plus is on the product side. Ce3 plus is also on the product side. So we are putting the product concentrations on the top. So the concentration of Cr3 plus on the top. There's no, the stoichiometric coefficient in front of it is 1. So we're just raising it to the power of 1. And then over here, Ce3 plus, which is the next term, so the concentration of Ce3 plus, and we have 3 in the front of it, so we are raising it to the power of 3. And in the bottom, we are writing the reactant concentration. The reactant is Ce4 plus aqueous, so we are putting that in the bottom, and there is a stoichiometric coefficient of 3 in the front, so we are raising it to the power of 3 over here. But there is no, you can see that this chromium over here is not there in this cube. Why is it that? Why is it that we've not included the chromium solid there? The reason is, if you remember our rules for writing reaction quotients and equilibrium constants, we never include pure solids, we never include pure liquids. So we don't include pure solids and pure liquids. Because chromium is a pure solid, we can include that in the denominator. Okay, so that's why we're not including the chromium. And so therefore, this Q is consisting of these 3 concentration terms, 2 of the product terms on the top and 1 reactant term in the bottom. They're all raised to the power of their stoichiometric coefficient. So if you have 1 as the stoichiometric coefficient, it's raised to the power of 1. If you have 3 as the stoichiometric coefficient, it's raised to the power of 3. So this is the equation that we get for solving this problem. And also, we should pay attention to these other terms. So all I've done here is plugged in the value of R, 8.314, plugged in the value of T, which is 298, and then the number of electrons is 3, and then it's multiplied by the Faraday's constant, which is 96,485. And then I have plugged in the value of delta E naught for as 2.34, because that's what we got over here. So I'm plugging that value into that equation. Now, all we have to do is just simplify this equation. So I'm just rewriting the same stuff, and then we plugged in the values. So here we go. So now, then we're going to simplify this. So we just put this particular thing in the calculator, this fraction in the calculator, and then see what we get. When you put it in your calculator, this fraction is going to come out to be 7.81 times 10 to the negative 6. This fraction over here is going to simplify to this value over here, 0.00856. And we take the ln of 7.81 times 10 to the negative 6. If you take the ln of that, is going to come out to be negative 11.76. So that's just this term over here that simplifies to 11.16. And then you multiply all of these things together. And when you multiply all of these things together, you're going to get, so you can see that this 0.00856 times negative 11.76, that comes out to be 0.101. And 0.101 plus 2.34 is going to give you 2.44 volts. So the delta E naught, which is the net potential of your reaction under non-standard conditions, is 2.14. Okay, so what this is saying is you could use certain concentrations of chromium 3 plus, Ce3 plus, and Ce4 plus. You can decide how much concentration you want in your solution. You can use that also to control the net potential of your cell. Okay, so that's what we're learning from this problem. So in this problem, we have learned how to figure out 2 things. We learned how to figure out the net potential of the cell under standard condition, which turned out to be this value 2.34. And then we also learned how to figure out the net potential under non-standard condition, and that value ended up being positive 2.44 volts. Okay, so that's what we learned in this particular problem.